Good morning. I'm going to use this situation to do a whole bunch of videos, I think. Initially, I was thinking about what can I do with this, and I was going to do one thing. Then it's like, that's not going to help teenagers or people learning calculus. So you're given a graph of a function on a closed domain. And then they typically, sometimes they'll tell you this, sometimes they won't. It's composed of a semicircle and two line segments, and by observation, you can see it's continuous on the entire domain. You can see that we have a technology problem there because it doesn't graph that point. This is a semicircle, but it doesn't look like a semicircle because of pixels. Okay. So the first thing this can be used for is testing the meaning that, do you understand the conceptual meaning of the definite interval on a finite interval? And when we look at this, now look at this function, you can see that this function is not positive. It's not zero or positive everywhere, because on this part of the graph it's negative. So this means that this is going to be a value because you have signed areas. This area is negative, this area is positive. Okay, sometimes we're going to test the meaning of the conceptual meaning of the Fundamental Theorem of Calculus. And we're not going to use antiderivatives. Some parts of Fundamental Theorem of Calculus. Okay. Now, in another video, what I'll do is I'll take this graph and I'll add more to it. So, you know what? I forgot a couple things. If I'm going to test the meaning of a definite integral, I can look at properties of the definite integral. And the way I'm going to do that is I'm going to apply properties of definite integrals. Okay. Now, if they're going to use a semicircle, they're going to be very careful. First of all, they may give you a domain that cuts to there, so you have a quarter circle. They're not going to give you something where you have to find an antiderivative, because this type of problem is used for both AB calculus and BC. BC calculus, you can use some integration techniques and get that area. But again, there's something called time. So the first thing we're going to start with is some properties of the definite integral. So one of the things they may ask you to do is they may say, hey, compute the, now you look right here, g of x is 0 to x of f of y in y. And they may say, find g of 0. And now we're going to go from 0 to 0 of f of y in y. If you think about that, you're integrating it at one point. F of 0 is 0. The width of the interval is 0, and there is a property that says if you're integrating a continuous function if f is continuous on a closed and bounded interval, and if f is defined at a, and you're integrating from one point to itself, that is 0. Why is it 0? Because conceptually you have a degenerate rectangle. You have a width of 0 and a finite height. In our case, our height is 0, and our width is 0, so that's 0. Okay. Now, they're typically going to ask you to do some evaluations here. Now, there's some other things. Maybe I'll slip that one in. Let's do the integral from, let's do g of 4. So that will be the integral from 0 to 4 of f of t and t. And if you think about that, 0 to 4, imagine in your mind you drop a perpendicular. Okay, I see a right triangle. If my memory is correct, the area of a triangle is 1/2 the product of its base and height. So this young adult is going to go, that's 1/2. I have a base of 4, and I have a height of 1, 2, 3, 4, 5, 6, 7, 8. So half of 32 halves, so 16 square units. Okay. So Let's also do g of -3, because that's another integral property there. Because now a lot of kids are going to look at this and they're going to, I'm going to switch the integrands because, right, the upper and lower bound of integration, well, 0 is larger than, don't do that. Just write it as it is to start. We're going to go from 0 to -3 of f of y in y. Well, we have a property that says if you're integrating a definite integral, if you switch the limits of integration, you multiply the integral by -1. Now, the reason why this is working is if you think about it, for this definite integral here, the widths are b minus a over n, because there's a Riemann sum running in the background, a limit of 1. Over here, it's a minus b. If you factor a -1 out, it'll be -1 times b minus a over n. That's the y. So here, -1, the integral from -3 to 0 of f of y in y. Now, hold on one second. That is a quarter circle. It's a negative area. But if I multiply it by -1, it becomes a positive area. That's one of the reasons why I wanted to throw this in there. -1, and I believe the area of a quarter circle, if my memory is correct, is 1/4 pi r squared. So -1, don't forget the pi over 4 like I just did. The radius is 3, and it's underneath, so it's negative. A negative times a negative is a positive. 3 squared is 9. I know some of you still write 6, but it's 9. Okay. I'm going to slip one advanced topic in here. Okay. The other thing this can be used for is to test the extreme value theorem. Okay. And remember, if you're going to use the extreme value theorem, you use the 1-2 combination. This guarantees you the extreme value, and then you're going to apply the candidate's theorem. So now notice I am slipping in other theorems as we go, and I'm trying to intentionally make this so it's not too long. Wait a minute, but Mr. I, wait, 1 second. Is f continuous? It is. Therefore, the accumulation of area is continuous on the closed interval from -6 to 8. So that means g of x is continuous because we just walked through the logic. Okay, so hold on 1 second. So g of x is continuous on the closed interval from -6 to 8. By the extreme value theorem, there is a global min and a global max. Okay. So now I have this thing called the candidate's test. The candidate's test says, when you have a function that's continuous on a closed interval, here's how you find the global extrema. You take the endpoints. Boom, boom, there they are. And you take the, I need the critical points. So the critical points of G are where, now in our case, G prime of X is 0, or G prime of X does not exist for, now we're going to look at the open interval. And I can hear some kids say, but Mr. Wright, wait 1 second. You don't need to worry about the endpoints because they're already candidates. They're endpoints. Now, that means I need to talk about the second part. Well, okay, some people call this the second part. Your book calls it the first part. It says if you have the derivative with respect to x of an accumulation function, it's that. So for us, let me pause this and turn it over. So for us, the derivative of g is called g prime, but I would still like you to work on notation, please. So please write this down. I'll start putting other things later on. So for us, that's f of x. So I'm going to come over here and say g prime, and this is a habit you may want to get into. So I need to find the critical values of g prime. When I look at this, do you see any breaks in that graph? No, I don't. So g prime exists everywhere in the domain. So I need to find zeros. So g prime of x, which is f of x, equals 0. Oh, x is 0. Why? Because I read the graph. Yes, it's also 0 at -6 and 8. I guess, okay, I'll make you happy. I'll put those in, even though that's really the one I want. Okay. So my candidates are x equals 0, -6, and 8. Okay. Previously, we've shown that g of 0 was 0. G of 8 is the integral from 0 to 8 of f of y in y. Okay. Is that, ladies and gentlemen, an isosceles triangle? It is. The base is 8, the height is 8. So 1/2 of 8 times 8, 64 cut in half, I think, is 32 square units. Okay. G of -6 is the integral. I still want to do this. I want to switch them immediately, but don't do that. Okay. Which is -1 times the integral from -6 to 0 of f of y in y. Now I look at this. This is a negative area. If I multiply it by -1, it becomes, oh no, we've got two positive areas. Okay, so -1, okay, and -1/2, don't forget the pi like Mr. Isaac, times 3 squared. A -1 times itself is 1. 9 times pi is 9 pi cut in half. Okay, this is between 3 and 4. Let's call it 4. Okay, I don't have to. That would be 36 cut in half. This is around 18, but smaller. So there's your global maximum, and there's your global minimum. My global maximum value for g of x is g of, oops, I almost wrote the wrong number down there, g of 8, which is 32 square units. How about the global minimum of g of x is g of 0, which was 0. Actually, you know what? I shouldn't put square units because these are just values. My bad. Okay. There you go. And now notice, that's 13 minutes. And I have only scratched the surface of what these problems do. So you'll see more graphs of this. I'll probably shrink them in the next one so I can write more on the paper. If you learned something from this, leave a comment.